so let's talk about what happens when a liquid or transforms to a gas, or a solid transforms into a liquid. I have here this heating curve, and this really is emblematic here in this picture. Let's say I have water in a pot, and I'm trying to make pasta or something, so I'm boiling water. So I'm starting at 25 degrees Celsius, and I throw a thermometer in there to see what the temperature is. As I'm heating up the water, the temperature of the thermometer is going to rise. I'm going to see it slightly rising until I get to 100 degrees Celsius. Once I hit 100 degrees Celsius, the temperature will stop rising. It will stay at 100 degrees Celsius until my entire liquid vaporizes. And it is shown here on this graph as red. Okay? And in this red zone here, I am still providing heat from the fire here to the water, but all the energy that I'm providing is going into transforming my liquid into a vapor, is breaking all the intermolecular forces of the liquid and transforming all of them into the vapor state. So the heat is still going into my liquid, but I can't see it on my thermometer. It's hidden from me. For this reason, we call the heat in this red zone the latent heat, L-A-T-E-N-T. L-A-T-E-N-T. It's a word, it's a regular word in English, it just means hidden. It's a good GRE word. And it's hidden because I cannot see the thermometer rising during this time. Here I can see it, and it is not hidden from me, and the thermometer is indeed rising. Here it is not. Okay, what does this mean for me? Well, we talked previously how we can calculate the heat change that you see when you heat something up. If temperature goes from temperature 2 to temperature 1 to temperature 2, how can I calculate the heat that has to be provided or that's being emitted? That actually assumed that there was no phase change. There is a phase change. We have to include the latent heat, and also we have to recognize that the specific heat of the liquid and the specific heat of the gas are going to have two different values. And I think doing an example is really going to show you how this is done. So let's look at an example. Let's say I want to determine the heat that's required to raise the temperature of 1 mole of methanol from 25 degrees Celsius to 100 degrees Celsius. And I'm giving you here that the boiling point for this thing is 65 degrees Celsius. So the latent heat here is 208 kilojoules per mole. The specific heat in the liquid state is 81 joules per mole, and the specific heat in the gas is different. As you can see, 116. And the way we will do this, and this equation will appear the most general equation appears in your reference sheet as well. It's this number of moles times the Cp in the liquid, okay, times T boiling minus T1. Okay, so I'm a liquid up until I hit boiling. Then I have to add the latent heat. Then I have to add the gas. And from T2 to T boiling, because I'm a gas between T boiling and T2. Okay, cool. So let me just substitute all the values in. I have 1 mole, which is convenient. Show that on purpose. My Cp for the liquid is 81. Okay, and I'm going from 25 degrees Celsius to 65 degrees Celsius. Okay, then I have to do the latent heat stuff. So again, I have 1 mole. Okay, the latent heat of vaporization is 208 kilojoules per mole. And then I'll do the gas. So I have 1 mole. Cp of the gas is 116 joules per mole. and then T2, I'm going to 100 degrees Celsius, and then I subtract the boiling point, which is 65, approximately. Okay, so let me just get the numbers. If you punch it into a calculator, this here becomes 3240 joules. This here becomes 208 kilojoules. Note that I have joules and kilojoules, and I have to do a conversion here. And then this is 4060 joules. So I'll just quickly convert this to joules. Like this. So this is 208,000 joules. So I'll need to replace this with this. So my Q at the end is 3240 plus 208,000 plus 4060 joules. And my final answer should be, with sig figs, 215,000 joules. There's a 3 here, but I dropped it because of sig figs. Okay, so hopefully this makes sense.